Okay guys, so this video is to quickly go over the quiz review for the exponents, perfect squares, and sequences. It's the quiz you guys are going to have Monday, so this will serve as a good little weekend review to help prepare you for that quiz. Okay. So starting off, talking about exponents, and an exponent tells you how many times a number or square root is used as a factor. Okay. You call a number that is expressed as an exponent a power. For instance, you read 10 thirds as 10 to the third power or 10 cubed because it has the little 3 as the exponent. And you can simplify an exponent by writing it as a product. So meaning you solve it. Okay, so down here it says simplify the following. You had 4 raised to the third power, which is the same as saying 4 times 4 times 4, or 4 times itself 3 times, or whatever number the exponent is. Okay. So working that out in a calculator, which you guys can all use, you would type in 4 yx and then 3. And that will give you an answer of 64. Okay, so again, if you were to do that in a calculator, you would type in your base number, which is 4, push the exponent button, which is the yx button, and then your exponent, which is 3, and you get an answer of 64. Okay, moving on to the second one, example B. You have 2 raised to the 5th power, which is the same as saying 2 times 2 times 2 times 2 times 2 in repeated multiplication form. But instead of working that out, just put it in your calculator. 2, your base number, yx, and then your exponent 5. And you get an answer of 32. Now number 2 wanted you to write 8 cubed using repeated multiplication. So all you're doing is writing that number out long ways with multiplication. So you have 8 as your base number, that's the number you're multiplying, 8, and 3 is your exponent, so you're doing 8 times itself 3 times. So 8 times 8 times 8. And that's how you write it out with repeated multiplication. Now, vice versa, number 3 wants you to write this expression that's written using repeated multiplication using an exponent. So all you guys need to do is identify which number is going to be your base number, which is the number you're multiplying, which in this case is 6. And then you count how many times you're multiplying that number by itself, and that's your exponent. So you have 1, 2, 3, 4. So the following expression will be written as 6 to the 4th power using an exponent. Okay. Moving down. Number 4, when did you explain why 2 cubed or 2 to the 3rd power is different from 3 squared? And the answer could be as simple as the fact that their answers are different. If you wrote out 2 cubed, you would write it out like 2 times 2 times 2, which gives you an answer of 8. And if you simplified 3 squared, or wrote it out with repeated multiplication, it would be 3 times 3, which would give you an answer of 9. Okay. So these two are different in that they give you different answers. That could be your answer. The answers are different. Okay. Alright, number 5. All you're doing, it says, what's the value of 5 squared plus 2 squared? When you encounter problems like this, you need to go ahead and square or raise whatever base number it is to its exponent, and then add or subtract or do whatever operation it's telling you to do. So in this case, you would do 5 squared, which is 25, plus 2 squared, which is 4, and you get an answer of 29. Very similar, number 6. What's the value of 3 cubed times 2 squared? So again, go and compute or apply the exponent. So in this case, 3 cubed gives us 27 times 2 squared, which is 4. Multiply these two numbers together, and you get an answer of 108. Alright, number 7, same thing. You have 12 raised to the first power, which is just 12. And I'll make note of that any number raised to the first power is just that number. If we did 1,000 to the first power, it's just 1,000. Okay. And then 82 raised to the 0 power, which is just simply 1. And that's another rule to point out, that any number raised to the 0 power is just 1. For instance, 1,000,000 raised to the 0 power is just 1. Okay, so for this one, 12 times 1 should have given you a product of 12. Okay, number 8, simplify 5 raised to the 0 power. And same rule applies here as with the 82 raised to the 0 power. It would just simplify to 1. Doesn't matter what number is in the base there. If you raise it to the 0 power, it is just 1. Number 9 is just writing 2 ways that this exponent could be read. So one way you could say is 8 squared, because we're raising it to the second power. And another word for raising any number to the second power is squared. Or 8 to the second power. Pretty easy. Alright. Going to the back side. And this one, you're just given an exponent, 5 squared, and you're identifying what the base is and what the power or exponent is. And then you go ahead and find the value of the expression. So in this one, and in any exponent, the base is the bigger number. And in this case, it's 5. And the power is the same thing as the exponent, which in this case is 2. And if you found the value of that, the same as saying 5 times 5, you get 25. Alright, so to square a number means to multiply it by itself. So for instance, 4 squared is the same as saying 4 times 4. You guys have already seen examples of that. Now the opposite of squaring a number is finding the square root. And the square root of a number is a number which, when multiplied by itself, produces the given number. Okay. For instance, the square root of 16 is 4, since 4 times 4 gives you a product of 16. Okay. So squaring a number and finding the square root of a number are inverse operations. Alright. So moving down these keywords here. Perfect squares are the numbers that result from multiplying any whole number by itself. Okay. For instance, 4 is a perfect square because you can multiply 2 by itself and get 4. 9 is a perfect square because you can do 3 times itself and get 9. 16 is a perfect square because you can do 4 times itself and get 16. And then 25, you guessed it, is a perfect square because you can do 5 times 5. And they just keep going up from there. So the symbol which means square root is this check mark. And it's the same on your calculator pretty much, except it's got a variable x underneath it, which normally would be a number that you're finding the square root of. Okay. So naming all the 2-digit perfect squares, they are as follows. You have 16, which is 4 times 4, 25, which is 5 times 5, 36, which is the result of 6 times 6, 49, which is the result of 7 times 7, 64, the result of 8 times 8, and 81, the result of 9 times 9. Alright, question 12, it asks, is 144 a perfect square? Now just as a quick little review, you can figure out if a number is a perfect square in your calculator. Okay. All you do, put in that number, and then press the square root button, which looks like that. It's got the check or the square root sign with the X underneath it. And then hit enter if the answer doesn't show up. And if you get a whole number, meaning a number that does not contain a decimal, then it is a perfect square. So in this case, yes, 144 is a perfect square. That's because the square root is a whole number or does not contain a decimal. It's the same idea. A whole number is any number that doesn't have a decimal in it. Okay. So for number 13, its S is 18 a perfect square. So in your calculator you type in 18, press the square root button, and you should get a pretty ugly decimal. And it should be about 4.24. Since that answer contains a decimal, you would say no. 18 is not a perfect square because the square root has a decimal, or it is not a whole number. This would be the square root of 18. Okay. Alright, and so the last questions on here, you were just finding the square root of each number, and each of these was indeed a perfect square. So square root of 400, just plug it into the calculator, 400, square root button, and you'd find the square root of 400 is 20. And to check it, you could take the square root, you do 20 times 20, and you get 400. Okay, next one, square root of 729, go and type in 729 in the calculator, push the square root button, and you get an answer 27. And the last one, square root of 121, plug it in the calculator, square root button, the square root of 11. Alright. Now we're going to move on to sequences, and this might not have been on the quiz review you guys got, but it's a real good review. Okay. Alright. Talking back about sequences, you have two types. You have arithmetic, and you have geometric. In arithmetic, you are adding as the common rule. Okay. Again, think A, arithmetic, add. Okay. And in these sequences, you find the common difference. These are just keywords to remember. So again, in arithmetic, you are adding as your rule. For example, here's a sequence. I've got 2, 8, 14, 20. This is an arithmetic sequence because I'm adding 6 to each of my terms. Okay, and so therefore my common difference was plus 6. Alright. In a geometric sequence, you find the common ratio. And in a geometric sequence, you're multiplying each term to get the next one. For example, 3, 6, 12, 24. In this geometric sequence, I'm multiplying each term by 2 to get the next term. So in this case, my common ratio would be times 2. And then you have to identify if it's arithmetic or geometric, if you're finding a common ratio or common difference, and what that common ratio or difference actually is. So take a minute and try to figure out what's going on here. How do you get from 5 to 15? And you know you're either multiplying or adding, since our numbers are going up in value. So take a second and try to figure that out. Alright, I'm going to move on. If you haven't figured it out yet, press pause. Okay. There are two ways you could get from 5 to 15. You could either add 10, okay, and that works. You do 5 plus 10, you get 15. Let's say you try to add 10 to 15. You do not get 45. You would get 25. So adding 10 cannot be the rule in this sequence. The only other way to get from 5 to 15 is multiplying by 3. And if we do 15 times 3, we do get, in fact, 45. And if we do 45 times 3, we do get 135. So, we are indeed multiplying each term by 3. Now, since we are multiplying, this is a geometric sequence. And since it's just a geometric sequence, we are finding a common ratio. And our common ratio, which again is a fancy 6th grade way of saying the rule, is times 3. You're multiplying each term by 3 to get the next one. So filling in the next 3 terms in here, we would multiply 135 by 3, and we get 405. Multiply that by 3, and we get 1,215. Multiply that by 3, we get 3,645. And that's it. Okay. So you guys go and look at the next one. You can pause this video while you try to figure out what the pattern is and what is going on in that little sequence there. You have 11, 22, 33, and 44. Go ahead and pause it. And I'm going to move on now with working it out. So you could do 11 times 2 to get 22. But if you do 22 times 2, you do not get 33. So that cannot be the rule here, times 2. The only other way to get from 11 to 22 is if we add 11. And if we go and add 11 to 22, we do indeed get 33. And if we add 11 to 33, we do indeed get 44. So that's the rule or pattern that our sequence is following. Since we are adding, it's an arithmetic sequence, and therefore it's a common difference, which is the fancy way of saying our rule. And in this case, our common difference is plus 11, or that's the rule the sequence follows. So to find the next three numbers in that sequence, we just add 11 to each one. So 44 plus 11 gives me 55. 55 plus 11 gives me 66. 66 plus 11 gives me 77. So again, since we were adding here, adding 11 to each term to get the next one, it was arithmetic and also common difference. And that was letter B. And we were adding 11 to each one. And letter A, since we were multiplying each term by 3, it was a geometric sequence. And therefore it was a common ratio that we were finding. Okay. And that kind of wraps up our little lesson here. Okay. If you have any questions, just watch this video again, refer to your notes, and good luck on Monday. See you guys then.